Hello, George Diamond here. We're continuing our flipped video series. We just finished our first flipped video unit on limits and continuity. My students really liked the concept of the flipped videos. We'd watch the videos at night and they'd come in the next day and work on homework problems. And they really liked that, so they kind of asked that we do some more some more units in AP Calculus. Now we'll see what we can do. So we'll try to flip maybe the next unit here as we look at derivatives. But part of AP Calculus we're just not going to be able to flip maybe. But we're going to start off here with our next flip video. Now this is chapter 2. This is a little introduction to derivatives. Now at our school we use the Larson text, which is a later transcendennial text. So in my videos here, at least at the beginning, you're not going to see any logarithms or exponential functions. You see tangent, you see the trig functions, you'll see polynomials, etc. But it'll be later on that we'll be looking at logs and exponentials. But what we have here, this is the first, basically an introduction to derivatives. And what I have is my PowerPoint here. We're going to kind of work my students through the PowerPoint. Now what you won't see on the PowerPoint here, you're not going to see any examples. Now, those will be in the next video. So it'll be in part 2 of this first section. So in the Larson text, this is section 2.1, just an introduction to the derivative, right, and the general derivative formulas. Now we'll be looking at a couple things in this unit: the derivative and the tangent line in the textbook at section 2.1. After this, we're going to look at some basic differentiation rules and rates of change. So specifically in this unit, we'll be looking at the general power rule, product rule, quotient rule. Okay, also we're going to look at the product and quotient rules and higher order derivatives too. So second derivative, third derivatives, etc. So this is what we're looking at in this unit. Now we're going to stop about halfway through chapter 2. The second unit, we're going to look at the chain rule, implicit differentiation, related rates. So we're going to kind of break the chapter up so it's not quite so long. And we'll be giving us a unit test after we get finished with the product and quotient rules. Now, so to get us started, okay, a little bit about the derivative. Now, so we're going to look at a couple of essential questions to get us started. Okay, number one is I can find the derivative, or how can I find the derivative of a function? All right, so we're going to be introducing the derivative, and we're actually going to find some derivatives today. All right. Number two, how are differentiability and continuity related? So how are those related? All right. So let's start off. Now a little bit about calculus. Calculus grew out of 4 major problems. All right. So really 2 major problems, but I kind of describe it as 2 or as 4. But first, the tangent line problem. All right. So how to get the slope of a tangent line to a curve. Prior to the development of calculus, that was very difficult. At best, you could estimate the slope of a tangent line to some difficult curves. Second, velocity acceleration problems. All right, so this is the second issue that we're working on that they developed calculus for to assist with. Minimum maximum problems. Now minimum maximum, that goes back to the tangent line problem. All right, so that's connected to the tangent line problem, and it's still a major issue if you're looking for minimum maximum prior to the development of our graphing calculators. For most functions, to get the minimum or maximum, local maximum, etc., calculus was the easiest way to do it. And then last is the area problem. Now, area under a curve, that's going to be antiderivatives. That'll be later on in our course. So let's start off with the tangent line problem. All right, so a little bit about it. Now, first of all, the tangent line problem, credit for this problem is given to Sir Isaac Newton from England and Gottfried Leibniz from Germany, right? And a little bit about the history. Back when these major developments in mathematics and science were going on, France, England, and Germany were very competitive about who got credit for some of these major developments. And for years and years, England and Sir Isaac Newton claimed credit for the development of calculus. And in Germany, they claimed credit for it also. So apparently the two just developed calculus at the same time. So finally they just decided, let's let both of them have credit for the development of calculus, and that's how it stands today. So Newton and Leibniz are both given credit for the development of calculus pretty much as we know it today. Now, a couple things about tangent lines. So when we look at derivatives is basically just slope of tangent lines. Now, Some tangent lines are easy to get, so they're easy to find. For example, tangent line to a circle, that's easy. So for instance, if you've got a circle, you're going to find a line perpendicular to a radius of the circle, and then you can get the tangent line to that particular radius. So for instance, here's my circle, okay, here's my radius. Now to get a tangent line to the circle, we just have to draw a line perpendicular to the radius of the circle, and it would look sort of like this right here. So you get that right angle here. So something like a circle. Circles are easy to get the tangent line of. But other types of curves, these are much more difficult. Right? So much more difficult, particularly complicated curves. They're very difficult to get the slopes of tangent lines without using calculus. Right? So, for example, you look at something like this. So now a little parabola is not too bad. We can get the slope of the tangent line like right here. That has to be a horizontal line. We can find that pretty easy. But something like this curve. If you're looking for the slope of a tangent line, let's say at that point there, without calculus, it's a lot harder to do. So very difficult to do. So some curves, are very difficult without using calculus to find the slope of a tangent line, especially before the development of these calculators and before the development of technology like we have today. Now, the problem of finding the tangent line on a curve at point P boils down, to finding the slope of the secant line at point P. So I'll show you how this works with calculus to get the slope of a tangent line to a curve. Right? So now, if you can imagine a curve in the Cartesian plane, so something like this. Right? So this like something like this right here. Now, I'm going to let this point right here be x, and what we do with the derivative, we're going to come a little ways down from x. Let's set this point right here, or let's say x value here is going to be x plus h. So this number plus some h value, right? So just another quantity, if you will. Now, what we're looking for here, we're going to try to get the slope of the tangent line to the curve at point x. So if we were to sketch it, it would look something like this right here. So slope of a tangent line, okay, this is what we're looking for. Now, to get the slope of your tangent line using calculus now, what we do is we take x and x plus h, and we draw a secant line to the curve. So if you look at this, here's our secant line. So you've got your curve passing through this point and this point. So remember, a secant line intersects a curve at two different points. So this is our secant line. Now, let me show us how we're going to use the slope of the secant line to get the slope of our tangent line. Now, as you look at your curve here, you got our 2 points on our curve. Well, let's describe the slope. Let's describe the location of the points at these on the curve of these 2 points. So come over here. So you can see it coming up here. Now this point is x. So the y value is going to be f of x. Okay, this x value is x plus h. So this point out here, this y value is going to be the function at x plus h. All right. So the location of this point on the curve is x, f of x. Okay, the location of this point up here is x plus h and f of x plus h. All right. Now, we all know how to get the slope of a straight line. It's just y2 minus y1 over x2 minus x1. And that's basically what we're looking at here when we describe the slope of your secant line. So y2 minus y1 over x2 minus x of 1. So if you look at our secant line now, so I've got our 2 points, f of, this is x plus h, this is f of x plus h, x and then f of x. So think of this as, okay, this is x of, let's see, x2, this would be x of y sub 2, I'm sorry. So x2, y2. Okay, this point down here is going to be x1 and then y1. All right, so you look at as we describe our slopes now using our two locations now, our 2 points. And like I said, it's basically just using the slope formula. So we're going to subtract our y's. So when you subtract your y's, now we're going to get the slope. Okay, that'll be y2 minus y1. So the function of x plus h minus f of x. So in the numerator, this is going to describe our slope. Remember, this is nothing more than y2 minus y1. And then we're going to subtract our x value. So this would be x plus h, okay, minus x. And once again, this is nothing more than x2 minus x1. And in the denominator of our slope, this is what it will look like. Right, now what happens is when you describe the slope here, okay, the x values here cancel out. Those cancel, and that's going to leave us with with f of x plus h minus f of x over h. Now, those of you, I'm sure we've all had pre-calculus. Most of you should recognize this right here as the difference quotient in pre-calculus. This is the difference quotient. Now, so this is called the difference quotient. So in pre-calculus, most students have seen the difference quotient when they come to AP Cal. Now, this is where the calculus part comes in. Because let me show you how we're going to take the slope of this secant line and come up with the slope of our tangent line at x f of x, at this point here. So what we do in calculus, now we've already looked at limits. So what happens is, if you can imagine this h value getting smaller and smaller and smaller, what happens, this x value here gets closer and closer to x. So notice, as x gets smaller, all right, so you can see the x plus h comes towards x, so we're going this direction, towards this x value. So as x plus h gets smaller, now look at the new secant line here. Okay, the new secant line, this slope is going to be a little bit closer to what we want for our tangent line, or what we would expect for our tangent line. Well, it's coming a little bit closer. What if h gets even smaller now? We're getting, now look at this right here. Okay, now this is x plus h. Now you can see the third secant line is very close to what I drew for the tangent line. So we say as h gets smaller and smaller and smaller, that is, as h approaches 0, then the secant line, right, so we say the limit as h approaches 0 of the difference quotient. Right, so as h approaches 0, and it's getting smaller and smaller and smaller, right? Then that will actually become, or will give us, the slope of the tangent line. So you can see when you take the limit as h approaches 0, that will give us the actual tangent line at this particular point. So as you can see, as h gets smaller now, you can see the slope of the secant line actually becomes the slope of your tangent line. Okay, and this is it. So the slope of the line tangent to x f of x is this one right here. And this is basically the difference quotient that you looked at in pre-calculus, but okay, we're going to take the limit as h approaches 0. So as h gets smaller and smaller and smaller, we're getting closer and closer and closer to x. And as h approaches 0, that number gets smaller, then that will give us the derivative. That will give us the slope of our tangent line, and a derivative is simply slope. All right, so slope is derivative. So, come on over. So the derivative of x is given by this expression right here. Now this one we need to remember, right? So this is it. Okay, this is how we get the slope of a tangent line. Actually this will give us the general expression for the slope, or what would be a function for the slope. So f of x, or f prime x, equals the limit as h approaches 0 of f of x plus h minus the function at x divided by h, provided the limit exists. So the limit has to exist, right? In order for the derivative to exist. So provided the limit exists, you need to remember this. It's a very important formula. We'll be looking at some examples as to how to use this formula to calculate some derivatives later on, and how to find the slope of some functions at a particular point. Right. Now, let's take a look at some notations for the derivative. Right, so notations. Now, several different ways to indicate a derivative. Right, first, my favorite, f prime x. Right, so you look at f and then the little dot here, or the little slash x. Okay, this indicates f prime of x. Right, so that indicates a derivative. That's one way to do it. So if you're taking the derivative of f of x, now keep in mind, the derivative, if you have a function and you take the derivative of that function, well, the derivative of itself will be a function, right, with its own graph and everything. All right, and later on I'll show us what that means and how those are related. Okay, also, another way to indicate the derivative is dy over dx. What this indicates, this is the derivative of y, okay, with respect to x. Right, so the derivative of y with respect to x. That's another common indication for the derivative, and you'll see us, I'll use each of these quite a bit, in the course. Okay, sometimes you indicate the derivative of f of x like so, and some textbooks may use this notation. It's not as common now, but I have seen textbooks that it's indicated the derivative like that. But like I said, it's not very common. But then the last indication of the derivative is like so, y prime. So simply y prime, that indicates the derivative of y. So if you have y equals whatever, you take the derivative, right? The derivative function is y prime. All right, so we just indicate y prime. So these are all notations of the derivative, and we'll use most of these except for this one. All right, so you'll see each of these used to indicate the derivative in our class. Now, a little bit of a note about each of these notations, right? Some of them. Okay, first of all, dx does not mean d times x. All right, so it means the derivative of x. dy does not mean the derivative, it does not mean d times y. All right, so it does not mean d times y. Okay, dy over dx does not mean dy divided by dx. All right, so it's not a typical fraction. Unless it's convenient to think of it as a fraction. Sometimes it is convenient to think of it like a fraction, where you can, dy divided by dx, but it does not mean division. So sometimes we kind of treat it like a division if it's convenient to treat it like division, but typically, remember, it does not mean dy divided by dx. Okay, also, we'll note, df over dx does not mean df divided by dx, right? Unless it's convenient to think of it as division. Sometimes it's convenient to look at it like that. But just keep in mind, when you see the notation, dy over dx, that does not mean dy divided by dx. Sometimes we treat it like division because it's convenient to look at it like that. Now you look at d of x, f of x does not mean d over dx times f of x. This is not a multiplication, this is the derivative of f of x. It does not mean d over dx times f of x. Unless sometimes it may be convenient to treat it like it's a multiplication. Right. Let's take a look at an alternative formula. Now there's two formulas here that we use. Okay, you saw what's called the general longhand derivative formula. Well, sometimes if all we need to find is the slope at a particular point on a curve, okay, we can use what I call the alternate formula. Right? So alternative formula, if you will. And it goes like this. This is what it says. It says you take the Alright, so here it comes. So the derivatives at point C at some particular x value, take the limit as x approaches that number. Now the other formula uses as h approaches 0. So as h gets closer and closer to x, or as h gets smaller and smaller and smaller, then that gives us the slope of our tangent line. But in this case, the limit as x approaches c at some particular x value. Now, the limitation of this formula is that it does not give you a general expression for the derivative. It doesn't give you the derivative function, if you will. Okay, all this gives you is basically what your calculator will give you. If you do a derivative on your calculator, the TI-84s, they'll basically just give you the slope at that particular x value. Same thing with this formula here. All this formula will give you is the slope. If that's all you're trying to find is the slope at a particular x value, this particular formula can be pretty easy to use. Now, sometimes this formula is harder to use than the other formula. Now, I'll show you some examples in just a minute, or in the next video, rather. We're going to take a look at some examples. I'll show you how to use this formula and the other formula, and how to get the same slope using each one. Like I said, this has a big limitation. Okay, this will only give you the slope at a point. All right, and like I said, if you're looking for the actual derivative, the actual x expression of the actual function, then this won't give it to you. Once again, provided the limit exists. All right. But we'll be looking at this formula, so make sure this is the other alternative formula here. So let's put a little asterisk next to this. This is one of those formulas you need to know. All right. So just like the other one we looked at a minute ago. Now, a couple things about derivatives. Okay. In order for a function to have a derivative, so to be differentiable, a function has to be continuous and smooth. So it can't just be continuous now. Right? So in the last unit, when we're looking at limits in continuity, we saw to be continuous, the left-hand limit has to equal the right-hand limit, and that has to equal the function at a particular x value. But now to have a derivative, it has to be continuous. That is, no jumps, right? No jumps, no gaps, no asymptotes, and it also has to be smooth. If you have a sharp corner, the derivative won't exist at a sharp corner. So we've got some examples here. I'll show us the derivatives are going to fail to exist at each of these. First, you've got a sharp corner. So for instance, if you look at the function f of x equals the absolute value of x. So a lot of absolute value functions, they'll have that V shape. Well, right here at the corner, the derivative doesn't exist. Because if you look at the left-hand limit here, the left-hand limit, and this is the right-hand limit here, okay, these are not going to be equal to each other. So the left-hand derivative is not going to equal the right-hand derivative also. So at a sharp corner like that, you know, you're not going to have a tangent line. All right? So you can't have a tangent line. So if you got some absolute value functions like this, you know, at that particular point, the derivative won't exist. Now, other places on the function it will exist. Now, another instance where the derivative doesn't exist would be something like this. And once again, you can see this is a cusp. This is f of x equals x to the 2/3 power. And you can see right there, you got that very sharp corner here. This is called a cusp. No derivative at a cusp. So once again, it comes to a point, no derivative there. Another example would be something like this right here. If you have a vertical tangent line. So if you have a vertical tangent line, let me show you. This is f of x equals the cube root of x. This is the cube root of x. If you look at the derivative, let's say right here at 0, 0. All right, so right there. Okay, now remember the derivative is slope. All right, now if you draw a tangent line, the tangent line will actually cross the graph. So the tangent line will be this right here. Okay. Now, of course, you all know, you know, the slope of. Now, look at this this tangent line. And this is a vertical line. All right, so it's going to be a vertical line. The slope of any vertical line, if you look at the slope, is undefined. Okay, that means the derivative is also undefined. So you can't have a derivative. You know, the slope of a vertical line is undefined, so no derivative at this particular point. Now, other points on the curve, yes, you'll have a derivative. But right here, this is the one that students tend to remember the first two, but now they'll forget about this one right here. So let's put us a little asterisk next to this one. I want you guys to remember, okay, this right here. Okay, vertical tangent line. All right, so if you got a vertical tangent line, this is one of the instances where the derivative will not exist. Now, the last instance in which no derivative will exist, if you have a discontinuity. So you can see this one right here, so discontinuity. For instance, f of x equals a step function. So a step function like this, you can see the jump. The left-hand limit does not equal the right-hand limit. So once again, that's one of the conditions, right? To be differentiable, it has to be the left-hand limit has to equal the right-hand limit. So it has to be continuous, and it's definitely not continuous. So if you get an asymptote or a jump, like you see here, no derivative. Right, so there's no way you can get a tangent line to a curve like this. And like I said, the students remember these pretty well, except for the third one right here. So vertical tangent line, that's the most difficult for a lot of students to remember. So I want you to remember, kind of be watching for, if you got a vertical tangent line where it actually crosses your curve, like this one does, there's no derivative. All right, let's move on. Now, let's take a look at graphing a derivative. Now, take a look at the graph. Now, this is you go ahead and sketch our original function. So this is y equals f of x. Now, if you look at this function, okay, this is basically it's like a step function, a series of vertical lines. Now, what we're going to do is we're going to see if we can graph the derivative of this function. And like I said, this is kind of like a step function. You got 1, 2, 3, 4 vertical lines. All right. Then right underneath it, now we're going to say the derivative is going to be the slope of the original function. So underneath it, right underneath it, let's graph the derivative. Now, if I can, I'll see if I can include at least the original function here, maybe this in your guided notes. But if it's not in your guided notes, you need to go ahead and sketch this now. So you can pause the video and go ahead and sketch each of these from 0 to 9. And let's take a look at the derivative, though. If we're going to graph the derivative of a function like this, now we don't have we don't have the function itself. All we're looking at here is the graph. All right, so let's see how we go about graphing the derivative then. Now, first of all, so remember now, the derivative is the slope of your tangent line. All right, so what we got to do is you look at your curve here from, okay, the first component of the curve goes from 0 to 1, and then the slope of the line changes. So remember, the derivative equals the slope. So in order to graph the derivative of this function, we have to describe the slope of each of those straight lines. Remember now, slope in this case is simply rise over run. That's what we're going to use. So we're going to use rise over run to come up with a function for the derivative. All right. Now, as you look at this, as you look at the first part of the graph from 0 to 1, you can see that that line has a positive slope. Okay, well, let's describe rise over run. Now let's go going to the right 1 and then up 2. So to the right 1, it's a positive 2. So the slope here is going to be 2 over 1 or 2. So the first part of this function, this first section of the line, okay, the slope is 2. Okay, that means the derivative y prime is equal to 2. So that's your slope, that's your derivative. All right. Now, what kind of a line, what kind of a graph would we draw for y equals 2? Well, you only have the y variable, so I'm sure you guys will remember now, y equals any number is a horizontal line. So let's come down here. Now, I also want you to notice, also as you look at this now, at the end point here, the derivative will be defined, but you can see this corner right here. And you can see that sharp corner. At these corners, okay, the derivative won't exist. So we want to leave those open to indicate that the derivative doesn't exist at the corner. But at the endpoints, the derivative will exist. So to graph y equals 2 from 0 to 1, here comes the graph. I've got it on the PowerPoint here, so it's nice and pretty. And here it is. You can see the straight line at 2, from 2 to 1, is just a horizontal line, y equals 2. All right, so that's the first part of the graph. Let's do the other part of the graph. Now you look at the, erase this from here. Now let's get the slope. Okay, let's get the slope of our tangent line from 1 to 4. Now to get the slope of this tangent line, so let me erase this. Okay, to get the slope of this tangent line, we would have to go to the right and then up. So we're going to go to the right 3, then up 1. All right, so the slope here is going to be, rise would be 1, run would be 3. All right, so the slope is 1/3. That means the derivative is y prime equals 1/3, or 0.333. So if you look at the graph, now we're going to estimate it here on the graph. As you look at the graph where y equals 1/3, that's another horizontal line at 1/3. So you look at the second part of the graph. Now once again, I indicated this on the PowerPoint. The derivative is defined at the endpoints of a function on a closed interval. So this is closed. So this endpoint is going to be shaded in, but at the corner, as you come down, this is going to be open. Now the second part of the graph is going to be from 1 to 3, would be y equals 1/3. Right? So this is y prime equals 1/3. Okay? And this right here is y prime equals 2. Okay? Now let's do the next part. Now you notice from 4 to 6, okay, the slope is 0. Okay, that means the derivative is 0. So from 4 to 6, that's another horizontal line along the x-axis. So this will be open here and then open there. Right? So that, hopefully you can see it pretty well on the video, but you can see it's shaded in from 4 to 5, and it's open at each endpoint. Now let's do the last section of this graph. Now the last section, first thing you notice about the graph, okay, the slope's going to be negative. Right? So the derivative is going to be negative also. Right? And to describe our slope, we would come rise over run. This will be down, and then to the right like so. So let's see, we're going down 3. So this will be -3 for the rise, and going to the right 3 would be +3. So the slope, in this case, would be -3 over 3 or -1. Right? So as you graph the last section of the graph from 6 to 9, okay, this is going to be a horizontal line at -1. So you can see it down here, open and then closed at the other endpoint. So it'll be open at the corner, right? So no derivatives, open on both parts of the graph, and then closed at the other endpoint. So this is how you're going to graph the derivative. So this is the original function. To get the derivative, you have to get the slope. Now, if you're just looking at the graph like we have here, a series of straight lines, you can just do rise over run to get your slope, whatever you have to do to get your slope. But that's going to give us our derivative, and then from there, the derivative is actually a series of horizontal lines. Now, let's move on. Now, in our textbook, we've got a little theorem. This involves differentiability implies continuity. So this is, in your textbook, this would be theorem 2.1. And what this says, it says if f is differentiable at x equals c, then x is continuous at x equals c. So Basically what that means is if a function has a derivative, then it also has to be continuous. Right? So continuity or differentiability implies continuity. So if there's a derivative, then the function must be continuous also. So we can assume that it's continuous. Now, the question I want to pose, if you look at the converse of this statement, would the converse be true? If a function is continuous, does that imply that the derivative exists? So just because it's continuous. Now, if there's a derivative, now remember, according to our theorem now, it has to be continuous. Right? So if it's a derivative, we can assume that it's continuous also. But if it's continuous, does that imply differentiability? Now, remember earlier, we looked at y equals absolute value of x, right? If you look at that graph, you have that V shape. Now, the graph of y equals absolute value of x is definitely continuous, but the derivative doesn't exist here. So just because, so this is not true. So the second part of this, the converse of this would not be true. Just because the graph is continuous, that does not mean that it has a derivative. But if it does have a derivative, it is continuous. Like I said, the converse is not true. Just because it's continuous does not mean it's differentiable. You could have a cusp or a corner. Right? So a cusp or a corner or a vertical asymptote, right? Which you would not have a derivative. All right? So the converse of this would not be true. All right, next. A couple things to remember. Said a function is differentiable if it has a derivative everywhere in its domain. It must be continuous and smooth. All right, key here, it has to be continuous and smooth. All right. Functions on closed intervals must have one-sided derivatives defined at their endpoint. So if you got a closed interval, it has to have a derivative at the endpoint also, so a one-sided derivative. I know in AP Calculus, one of the most common mistakes is students, if they have they're given a closed interval, and they won't look or they won't consider the endpoints. Particularly when we get at minimum maximum values, finding minimum maximum occurs in particular curves. You know, if it's on a closed interval, students forget to check the endpoints, but you got to check the endpoints in a lot of cases. Okay, that concludes our video, and we'll do part 2 here with the next video.